how to derive the least squares estimate geometrically in hyperspace. And hyperspace is vast, it's hard to fix ideas. So we're gonna go back to Earth to 2 dimensions. And that also makes for a very simple example. If we want to project down, we can pretty much only go from 2 dimension to 1 dimension to make it easy. So we are projecting to 1 dimension. That means the model only has 1 beta value, and I'm choosing y equals beta 0. This model actually does not have any x variables. So our data also doesn't need any x. And well, we're projecting from 2 dimensions. That means I have 2 observations, and the data are here 4 and 6, right? So 2 y values. And as I said, no x because the model doesn't have any x. All right, so putting that into the equation, we have 4 and 6, and then we have the vector 1, 1, right, corresponding to the intercept, times beta 0 plus the residual. And we're looking to project from the 2 dimensions into a 1-dimensional subspace, and we are allowed to walk alongside this vector 1, 1, so a multiple of this vector. What is this vector in the graph? Well, you see the observation 1. You have 4. The observation 2 is 6. So we get the vector up here, right? We're going from the origin to up here. This is the blue vector. We are in the subspace allowed to march alongside the direction of 1, 1. Here is 1, 1. So we can extend that as much as we want, but the subspace is this one line, and we have to stay on this line. So mu or x beta must be on this line. We have shown that we go so far such that when we project the y down onto the subspace, we get a right angle right here at the subspace. So we know, given our derivation, or geometric argument, we know that we have to be right here. Okay, so if we look at the axis here, I'm gonna claim that this is the point 5. Look at here, 5, and there's another 5. So this is 5, 5. And we're gonna show that this is correct. How we're gonna show this? Because, well, if this really is the right angle, then the theorem of Pythagoras holds, and we have this squared plus equals this squared plus that squared, right? Because that only works if there's a right angle. So we have the mu here, and then the corresponding residual is, look at this, minus 1 plus 1, right? So minus 1 plus 1. Now, we don't know whether it's exactly minus 1 or minus 1.01 or something like that. I'm just gonna propose it's minus 1 plus 1 to get from here to there. And then we plug it into the theorem of Pythagoras. And if it's true, then it's going to come out all right. Okay. So the other thing is we can look at how many steps we march along this line to get to here. This is a 5. So it's 5 steps. 5 times the vector 1, 1 is going to land us exactly here, which means beta is 5. Let's look at that. Oh, that's the Stata code just for completeness. We have proposed the residual is minus 1 and plus 1. And actually, when we know the residual, we can already, beta must be 5 then here to make this work out, because the equation has to hold. 4 equals 5 minus 1, and 6 equals 5 plus 1. But now let's see whether we have the right angle. And so we're doing Pythagoras. So the long one here is 4, 6. So if we get the squared length of that, we get 16 plus 36 is 52. For the residual vector, we get minus 1 squared is 1, plus 1 is 2. And for mu, or x beta, which is 5 times vector 1, 1, or the vector 5, 5, we get 25 plus 25, which is 50. So the long one, if there is a right angle, the long one vector, the length should be 52 equals 50 plus 2. 50 plus 2 equals 52. So the theorem holds. That means we do have a right angle, which means this is the least square. If this is the least square estimate, of course, we should be able to get it much, much more easily through our formula, this one. So let's see whether that is true. What do we have in terms of the X matrix? Well, we don't have any X's, we just have the intercept. And we have seen that for the intercept, the X matrix consists out of a vector of ones, right? So here we have the vector of ones. We have only two observations, so there's only two elements, transpose 1 and then the inverse. If we multiply this out, it's going to be 1 times 1 plus 1 times 1 equals 2. Inverse is 1/2. Then we have these two vectors, and that just means adding up the numbers, which is 4 plus 6 is 10, divided by, or multiplied by 1/2 is 5. Done. All right, now your turn. This is a different example using the exact same model and the exact same projection in the sense that we're going from 2 dimensions to 1 dimension. Where are my 2 dimensions? Well, we have 2 observations for y, observation 1, observation 2. We don't have any x values just as before because our model just has the intercept. So, and by looking at where the vector ends, you can see what the values, what the 2 observations are for y. This does not correspond, the red things do not correspond to the least squares estimator because, well, there is no rectangle, right? So least squares, we need the right angle. That being said, it is an estimator, and so we can see what the estimator is by looking at the vector mu. So I want you to tell me what this estimator corresponds to, so what the beta is that corresponds to this mu. And as I said, it's not the least squares estimator. I will leave you to answer that, and I will go to the next page. And on the next page, I have the same graph. And now I'm asking, what is the least squares estimator? And you can answer that in one of two ways. You can either plug it in into the formula and calculate it, or you can sort of in your head or on a sheet of paper, you can move one of those lines such that you get the right angle, and then you can read it off the graph. And so I made that such that we have easy numbers here, and it's going to be one of those 5 numbers. And so you can read it off the graph directly. So either you use the least squares formula, or you move the 2 lines or one of the lines such that you have a right angle, and you get it then by reading off the graph. All right, this concludes this segment.